Far beyond our Milky Way lies the Cartwheel Galaxy, a dazzling ring shattered by a colossal galactic impact. But how could such violence create something so beautiful? In this video we'll journey through the mystery of its rings and hidden past. If you enjoy it, please like, subscribe and share, and tell us in the comments, do you think galactic collisions are more destructive or more creative? Thank you for watching. Now let's begin. Far from the familiar span of the Milky Way, in the direction of the constellation known as Sculptor, lies a small group of galaxies set against the dark background of intergalactic space. Among them, one stands apart in appearance and in history. This is the Cartwheel Galaxy, a vast and unusual system whose form has been shaped by a violent event in cosmic time. From a distance it presents the likeness of a perfect ring, bright around the edges and dim at the centre, as though a ripple had been frozen into the stars themselves. Yet this striking structure does not arise in isolation. It belongs to an environment of quiet companions, a modest gathering of galaxies bound together by gravity and situated hundreds of millions of light-years from Earth. In this remote cluster, the Cartwheel claims the role of the most massive and remarkable member. The setting in which the Cartwheel resides is not crowded like the dense heart of a large cluster. Instead, the group is relatively sparse, with only a few significant galaxies interacting within shared space. These companions provide important context, for they allow astronomers to reconstruct how the Cartwheel's current shape came into being. In surveys of the region, two smaller galaxies are seen close by, lying in positions that suggest past gravitational encounters. Their appearance is less dramatic, their shapes more ordinary, yet their proximity is key to understanding the larger system. They provide reference points showing what galaxies of this group might look like in undisturbed states. By comparing their structure and motion with that of the Cartwheel scientists, are able to piece together the story of how such a striking ring was created. The wider surroundings are calm yet not empty. Intergalactic space here contains diffuse gas and dark matter halos that stretch beyond the visible disks of the galaxies. This unseen matter plays a role in governing the slow dance of orbits that hold the group together. Each galaxy drifts through this common gravitational field, carrying with it the star's gas and dust that form its visible body. For billions of years, these members may have circled one another in relative peace, forming a stable configuration with little to distinguish them from countless other small galaxy groups scattered across the universe. It is only when an intruder arrives or when an orbit carries one member directly into another's path that dramatic changes occur. The Cartwheel's present form is the testimony of such a passage. The light from this system takes hundreds of millions of years to reach Earth. That means every observation is a view into deep time. The ring we see today was set in motion long ago, and the processes now unfolding within it are echoes of a moment already past. For astronomers, this is an opportunity, for the Cartwheel preserves the signature of collision in a way that is large, clear and measurable. It is not a faint distortion or subtle warping of a spiral arm, but a complete reorganization of an entire disk into concentric waves. To see such a structure at this scale is rare, and the clarity of its geometry allows scientists to compare observation with simulation, to test theories of galactic dynamics, and to track the long consequences of an encounter between giants. The outer ring, bright in optical light, draws attention immediately, but it is the placement of the galaxy within its small group that allows the story to be reconstructed. The companions offer hints of the culprit, the smaller galaxy that passed through and set the Cartwheel into motion. They also act as controls showing what happens to members that remain untouched by direct impact. Their disks still resemble familiar spirals, their star formation is more modest, and their shapes are not warped into rings. It is by contrasting these quiet neighbours with the Cartwheel's remarkable form that astronomers can isolate the effects of collision from the normal processes of galactic evolution. The environment is also marked by diffuse bridges of material, faint trails of gas, and stars linking the galaxies. These are signs of gravitational interaction evidence that matter has been tugged and stretched across intergalactic space. In the larger universe, such features are common in interacting groups where the pull of one galaxy disturbs the outskirts of another. Here they confirm that the Cartwheel's companions have not been distant observers, but close participants in a history of encounters. Such details reinforce the view that the present ring is not a chance alignment or optical trick, but a physical ripple spreading outward through a once orderly disk. From the outer context, astronomers draw not only the story of impact, but also the scale of the event. By measuring the speed at which the ring expands, they can estimate how long ago the collision occurred. By comparing the brightness of stars in different regions, they can estimate the ages of stellar populations formed in its wake. These estimates place the impact within the last few 100 million years, recent in galactic terms. This timing matches well with the separation of the suspected intruder galaxy from the Cartwheel today, suggesting that the smaller member has moved away after piercing the larger disk, leaving behind the concentric waves that still expand. The sculptor group itself becomes the backdrop for all of this. Without the framework of the group, the story of the Cartwheel would be harder to read. Isolated in intergalactic space, the ring might appear as a puzzle, without context, a form without explanation. But surrounded by its neighbours, the evidence of collision is preserved not only in the Cartwheel's unusual ring, but in the trails, distortions and alignments of the smaller galaxies around it. Together they provide a complete picture of a system in recovery from a transformative event. The study of such systems is not only about individual galaxies, but about the behaviour of matter under gravity on the larger scales. A galactic disk is not solid, but a collection of stars and gas orbiting a common centre. When disturbed, it behaves like a fluid rippling, compressing and stretching in response to an intruder. The Cartwheel demonstrates this vividly. Its ring is the outward ripple of compression, a circular wave that propagates through the disk, much as a stone dropped into water sends waves across a pond. This analogy, though simple, helps to convey the physics at play, for the galaxy's stars and gas respond to the impact with patterns that can be traced, measured and compared with models. Thus, the intergalactic environment sets the stage, the companions provide the context, and the Cartwheel itself stands as the central figure in a story of collision and response. From the outermost view, the sculptor group appears quiet, a small assembly bound by gravity and drifting together through cosmic space. Yet within this calm setting, an extraordinary transformation has taken place, producing one of the most distinctive galactic structures known. The evidence lies across scales, from the positions of the neighbouring galaxies to the diffuse bridges of matter between them, and finally to the dramatic ring that defines the Cartwheel itself. Each element adds to the account, showing how a single passage of a smaller galaxy through a larger one can leave behind a pattern visible across hundreds of millions of light years. In the quiet setting of the sculptor group, the Cartwheel Galaxy does not stand alone. Surrounding it are several smaller companions, their structures preserved with less disturbance, their light shining in forms more familiar to astronomers. Two of these companions are of particular interest. They are positioned close to the Cartwheel and show evidence of past gravitational influence. While their shapes do not display the striking ring that defines the Cartwheel, their presence is essential for understanding how the larger galaxy came to be so altered. They offer contrast and context, reminding observers what the Cartwheel might once have resembled, and what other members of the group still appear to be. One companion is relatively close in projection, lying to one side of the cartwheel, its shape still bearing the spiral arms that mark many disk galaxies. The other sits nearby as well, its appearance smaller and more compact but still distinct. Both appear as bystanders, yet their motion suggests that they are bound to the cartwheel through gravity and have interacted with it across time. Their paths and velocities help reconstruct the history of the group. If the cartwheel has been struck by an intruder, one of these smaller galaxies may hold the identity of that visitor now seen displaced, but still linked through gravitational bonds. Astronomers use spectroscopic studies to measure the speeds and motions of these companions relative to the cartwheel. By studying the redshifts of their light, they can calculate whether the galaxies are approaching, receding, or orbiting together. In the case of the cartwheel's companions, the results confirm that they are not mere foreground or background objects, but part of the same system. Their light shifts indicate motion consistent with shared membership in the sculptor group. This is crucial, for without such confirmation one might wonder whether the nearby shapes were coincidences of perspective, rather than genuine participants in the same cosmic event. These smaller galaxies, though less massive, exert gravitational pull that can affect the larger system. Over long periods, such pull can warp outer disks, draw out streams of gas, and create faint bridges of stars between members. Such features are seen here, supporting the idea that the companions have been part of ongoing interactions. Yet the most dramatic event, the one that produced the cartwheel's ring, required more than distant tugging. It demanded a direct collision, the kind where one galaxy plunges through the heart of another. By comparing the positions of the companions today with models of galactic dynamics, astronomers are able to identify which one most likely passed through the cartwheel setting, off the wave that continues to expand outward. The significance of these companions lies not only in their role as suspects, but also as controls. They allow astronomers to compare star formation rates, gas content, and structural details between disturbed and undisturbed galaxies within the same environment. In the cartwheel, star formation is vigorous and concentrated in the ring, while in its companions it's more evenly spread and more modest. This contrast shows how a collision can trigger starburst activity by compressing gas in specific zones. The companions also retain more orderly disks without the concentric ripples that dominate the cartwheel. Together, these comparisons make clear that the ring is not a natural stage of evolution, but a direct result of violent disturbance. High-resolution imaging from space observatories has revealed faint streams of material between the cartwheel and its companions, further evidence of interaction. These tidal features, as they are called, are made of stars and gas pulled out from the galaxies during close passages. In the case of the cartwheel, the most obvious tidal signatures are seen in the faint spokes and debris fields that radiate from the ring, but the presence of nearby galaxies with distorted halos adds weight to the picture of a dynamic history. The companion stars and gas have been stretched through less dramatically, suggesting that they too felt the force of the encounter even if they were not the main victim. The role of these companions also extends to the future. Gravitational systems like this group are not static. The galaxies will continue to orbit, to approach and recede, to interact and distort one another. Over billions of years they may merge into larger systems, losing their individual shapes. The cartwheel's companions thus represent both the past and the future, holding clues to what has already happened, and foreshadowing the long processes yet to unfold. Though astronomers avoid predicting meaning, they can measure the likelihood that these galaxies will remain gravitationally bound and continue their slow dance in the sculptor group for many ages to come. Observations across different wavelengths confirm that the companions have different compositions of gas and dust compared with the cartwheel. Radio studies reveal their reservoirs of hydrogen, the raw fuel for star formation, while infrared surveys trace the glow of dust warmed by stars. Compared with the intense emission from the Cartwheel's outer ring, the companions appear quieter with fewer regions of intense starbirth. This difference is another marker of disturbance, for it indicates that without a collision, a galaxy of this size might sustain a steady but moderate level of activity. The Cartwheel, by contrast, has been driven into a burst of concentrated star formation that sets it apart. The study of these smaller galaxies is therefore not secondary but essential. Without them, the evidence for collision would rest solely on the Cartwheel's current shape, which might invite alternative explanations. With them, the case becomes clear for their positions. Motions and features provide corroborating details. They are the silent witnesses of the event, present in the same group, showing signs of related interaction and serving as living comparisons of what a disk galaxy looks like when it has not been shattered into a ring. Astronomers continue to refine models of the Cartwheel's history by adjusting parameters such as the mass of the intruder, its angle of approach, and its velocity. The companions provide constraints for these models, narrowing the range of possibilities. For example, if one companion is moving away at a certain speed, the model must account for its present location as the outcome of a past passage through the Cartwheel's disk. If the other remains relatively undisturbed, then it may not have been the direct intruder. Such details sharpen the reconstruction, moving from general theory to specific scenario. In this way, the companions transform the Cartwheel from an isolated puzzle into a well-framed case study of galactic dynamics. Thus, the companions of the Cartwheel stand as more than background objects. They are part of the same small gravitational family participants in a long and complex interaction, and essential to explaining why one galaxy among them has taken on such an extraordinary form. Their continued presence nearby ensures that the history of the Cartwheel is not a mystery without context, but a story that can be read from multiple sources of evidence. In the stillness of the sculptor group, these galaxies drift together, their motions slow on human timescales, but decisive across cosmic spans. Against this backdrop, the Cartwheel's companions remind us that, even in quiet regions of the universe, encounters between galaxies can reshape their very structures and leave behind forms that endure for hundreds of millions of years. Within the sculptor group, the quiet background of intergalactic space frames a scene where one galaxy has been radically transformed, and the origin of that transformation lies in the approach of an intruder. The evidence of this passage is written into the Cartwheel's structure, but it is by careful measurement and modelling that astronomers identify how the smaller galaxy moved and what effects its trajectory produced. The intruder was not an equal in mass or size to the Cartwheel, but a smaller companion whose orbit brought it directly through the larger disk. Such a passage is rare, for the distances between galaxies are immense and direct collisions uncommon. Yet when they do occur, they leave behind signatures on scales that endure for hundreds of millions of years. The suspected intruder is one of the neighbouring galaxies seen today close to the Cartwheel. Its position and speed suggest that it once crossed the larger disk, plunging through the centre like a stone through still water. Unlike two stones which might shatter on impact, galaxies are mostly empty space between stars, so the collision does not involve direct star-to-star encounters. Instead, it is the gravitational disturbance that transforms the system. The mass of the smaller galaxy passing through at high velocity pulls on the stars and gas of the Cartwheel's disk. This creates waves of compression that spread outward, reorganizing the disk into rings. Astronomers studying such interactions rely on simulations that reproduce the dynamics of galaxy collisions. By adjusting parameters such as the speed of the intruder, its angle of approach, and the mass ratio between the two systems, they compare the resulting patterns with what is observed. In the case of the Cartwheel, these models consistently show that a near head-on collision is required to produce such a symmetric ring. Off-center impacts lead to arcs or distorted spirals, but the nearly perfect circle seen in the Cartwheel points to a direct plunge through the middle. The intruder galaxy, though much smaller, carried enough gravitational influence to send shockwaves through the larger system, setting the entire disk into motion. The approach of this smaller galaxy likely began with a long orbit. Bound by gravity within the group, it may have circled at a distance for billions of years, occasionally passing closer, but never directly through. Then at some point in the last few 100 million years, its trajectory shifted, bringing it into line with the Cartwheel's center. The speed of this motion is on the order of hundreds of kilometers per second, fast enough to cross the disk in a relatively short span of cosmic time. As it did so, it pulled stars inward during the approach, and then released them outward as it passed through, creating a wave that rippled across the disk. One of the striking features of such a collision is that the intruder does not necessarily remain inside the larger galaxy. After piercing through, it continues on its path, leaving the disk behind, but still linked through gravity. This is why astronomers can still see the intruder today as a separate companion positioned nearby, but no longer embedded within the Cartwheel. Its identity is suggested by its current motion away from the larger system, consistent with having passed through in the recent past. While the Cartwheel bears the visible scars, the smaller galaxy continues its path, its own structure disturbed but not destroyed. The gravitational effects of the encounter extend beyond the stars. Gas clouds within the Cartwheel respond strongly to compression, and it is this response that sets off the intense star formation now seen in the ring. As the intruder passed through, it generated a circular shock wave that moved outward through the disk, sweeping up gas and dust, compressing them, and triggering collapse into new stars. The light of these young stars now outlines the ring, a bright frontier expanding across the galaxy. Without the intruder, this wave of activity would not exist. The normal evolution of the Cartwheel would have resembled a spiral galaxy with star formation spread across arms, rather than concentrated in a ring. The speed of the intruder's approach and its angle of passage are critical to the outcome. Too slow a crossing and the two galaxies might merge rather than producing a ring. Too angled a path and the resulting distortion would not form a symmetric wave. The near-central impact observed here is a case that produces one of the most distinctive outcomes, a ring galaxy. Such systems are rare, and the Cartwheel is among the clearest examples, making it a key subject for study. By examining its structure, astronomers not only learn about this particular event, but also refine understanding of how gravitational interactions shape galaxies more broadly. The intruder itself, while smaller, is not insignificant. Its mass is enough to drive waves across a system tens of times larger, yet it survives the encounter, its stars continuing to orbit their own center, its gas and dust disturbed but not destroyed. The asymmetry of scale between intruder and victim is a reminder that even a smaller galaxy, when moving at high velocity, can profoundly reshape a larger disk. It is not always the most massive member of a group that dictates the course of events, but sometimes the one that passes directly through. Today, the separation between the Cartwheel and the intruder is a measure of time since the event. By calculating how fast the intruder has moved since passing through, astronomers can estimate when the collision occurred. This provides a timeline that aligns with the age of stars in the ring, many of which formed within the last few 100 million years. Together, these independent lines of evidence strengthen the conclusion that the intruder's passage is the cause of the Cartwheel's unusual structure. The approach of the intruder is thus the pivotal moment in the history of this system. It turned a spiral galaxy into a ring set off bursts of star formation and created patterns of debris that extend far into space. Though the smaller galaxy continues on its way, its influence is preserved in the Cartwheel's current form. For astronomers, this makes the Cartwheel not only a striking image, but also a dynamic record of how galaxies interact. By studying the details of the intruder's approach, its speed angle and effect, scientists gain insight into processes that shape galaxies throughout the universe. From the perspective of the Sculptor group, this event is one episode in a longer story. The galaxies of the group remain bound by gravity and will continue to interact. The intruder may orbit back in the distant future, perhaps setting off further waves of disturbance. But the specific passage that produced the Cartwheel's ring is a unique moment preserved in the patterns we see today. It is the evidence of a direct approach, a plunge through the disk that rearranged stars and gas into concentric circles, and it remains visible hundreds of millions of years after the event itself. When the smaller galaxy finally passed through the Cartwheel, the encounter unleashed a transformation that would define the system for hundreds of millions of years. The crossing did not destroy the stars themselves, for the vast distances between individual suns meant that direct collisions were almost non-existent. Instead, gravity became the force of change. The intruder's mass pulled on the disk as it plunged through compressing gas and shifting orbits, then releasing them outward in a wave that travelled across the galaxy. This wave of motion is what astronomers identify as the collision's most striking signature, the expanding ring that today outlines the Cartwheel in a circle of light. The physics of this process can be compared to ripples in a fluid, though the material here is stars' gas and dust rather than water. The disk of a galaxy is not rigid. Its stars orbit in organized paths around the center, but the arrangement can be disturbed by sudden forces. When a gravitational intruder crosses the center, the disk responds as a whole. Inner stars shift inward under the pull, while outer stars are set into outward moving trajectories. The result is a circular wave, a density front that sweeps across the disk, carrying with it the compressed matter that becomes the visible ring. This process is known as a collisional ring formation, and the Cartwheel is one of the clearest examples known. The expanding ring is not a solid structure. It is a moving front of density, a region where stars and gas are crowded together compared with their surroundings. As this front travels outward, it leaves behind older stars while pushing gas clouds into new alignments. The stars formed earlier remain in place while fresh generations are created along the advancing edge. This creates a sequence of stellar ages across the galaxy, with younger stars at the rim and progressively older populations toward the center. Such a gradient offers astronomers a record of the timing and speed of the wave, allowing them to reconstruct how long it has been since the collision began. Measurements of the ring's current size and its rate of expansion suggest that the collision took place a few 100 million years ago. This is recent by galactic standards, where lifespans are measured in billions of years. The ring itself expands at several tens of thousands of kilometers per second, carrying the density wave steadily outward. This speed is not uniform. It varies with the distribution of mass and gas within the disk. By tracking these variations, astronomers learn not only about the impact, but also about the Cartwheel's original structure before the event. The ring thus serves as a probe into the history of the galaxy, revealing both its present state and its past arrangement. The circular symmetry of the Cartwheel's ring points to a nearly central collision. In many interactions, when the path of the intruder is offset, the result is a symmetry. One side of a disk becomes warped. Arms are stretched into tails or arcs form rather than full circles. In the case of the Cartwheel, the ring is remarkably even, extending as a nearly perfect loop around the galaxy. This strongly indicates that the smaller galaxy passed through the center, or very near it, ensuring that the gravitational disturbance radiated outward evenly in all directions. The clarity of this geometry makes the Cartwheel a particularly important subject for study, as it provides one of the best natural laboratories for understanding collisional dynamics. The expanding wave does more than rearrange stars. It also compresses the interstellar medium, the gas and dust that lie between stars. This compression triggers star formation, lighting up the ring with bright clusters and associations. These newborn stars are massive, hot and luminous, making the rim of the Cartwheel shine brightly in visible light. Observations confirm that many of these clusters are young, only a few million years old, formed as the wavefront passed through their region. Behind the ring, older stars remain less luminous in the visible spectrum, while the core shows signs of having been stripped of much of its gas, leaving it relatively dim compared with the blazing rim. The impact also set off waves in different components of the galaxy at different speeds. Gas clouds respond more strongly than stars as they are more easily compressed. Dust is carried along as well, glowing in infrared when heated by nearby young stars. These multiple responses create a layered structure across the Cartwheel, with visible infrared and radio observations each tracing different parts of the expanding wave. Together they confirm the dynamic nature of the ring, showing it not as a static band, but as a moving front reshaping the galaxy from the outside inward. The inner regions of the Cartwheel are left in a transitional state. While the wave has passed outward, the center retains older populations of stars with fewer signs of recent formation. The contrast between the bright ring and the dimmer core underscores the disruptive power of the collision. Once a spiral galaxy with arms likely similar to its neighbors, the Cartwheel has been reorganized into a hollowed system where star formation is concentrated at the edges. This redistribution of activity is one of the hallmarks of a collisional ring, and it marks the difference between the Cartwheel and more ordinary spirals within its group. Astronomers continue to study the expanding ring, not only to understand the Cartwheel itself, but also to refine models of how galaxies evolve through interaction. Such collisions are not rare in the long history of the universe. They occur whenever orbits bring galaxies together, and the results can range from subtle warping to complete mergers. The Cartwheel demonstrates one possible outcome, the creation of a symmetrical ring that records the details of the passage. By comparing theory with observation, here scientists can improve their understanding of similar events elsewhere, even in more distant systems too faint to observe in detail. The ring also serves as a natural laboratory for studying star formation under extreme conditions. The compression at the wavefront is intense, leading to bursts of new clusters that may not occur in such concentration under normal circumstances. By measuring the ages, masses, and distribution of these clusters, astronomers can test theories of how stars form in response to pressure waves. The results show that collisions can dramatically accelerate the pace of starbirth, turning a galaxy into a starburst system where thousands of new suns ignite in a relatively short span of time. Thus, the expanding outer ring of the Cartwheel is more than a visual feature. It is the record of a violent event and a dynamic process still unfolding. It is the moving frontier of change marking the passage of a smaller galaxy that set off waves across a much larger disk. It is the site of intense star formation glowing brightly in multiple wavelengths, and it is the key evidence by which astronomers reconstruct the timeline of collision from the moment of impact to the current state of expansion. The ring defines the Cartwheel today, shaping not only its appearance, but also its internal processes, and it will continue to move outward until the wave has spent its force leaving behind the patterns of stars and clusters created in its wake. Radiating inward from the luminous rim of the cartwheel, faint but distinctive structures stretch like fragile spokes between the outer ring and the inner core. These features give the galaxy its name, for they resemble the connecting lines of a wheel. At first glance they appear delicate, but closer study reveals that they are evidence of the intense gravitational forces that tore through the disk during the collision. These spoke-like formations are not random streams. They are coherent bridges of stars, gas and dust sculpted by the combined effects of tidal forces and wave dynamics as the density front expanded outward. The spokes are most easily seen in high-resolution images taken in visible and infrared light. They appear as faint streaks that cross the otherwise empty interior of the ring, linking the bright rim to the dim central regions. Their origin lies in the interaction of stellar orbits with the expanding wave. As the ring moved outward, some stars and gas were left trailing behind, caught in paths that connected outward motion, with residual inward pull. The result is a set of elongated filaments that cut across the hollowed interior. They are not uniform in brightness or density, but patchy and irregular, suggesting that different populations and gas clouds were caught in different ways. Gravitational simulations show that such spokes arise naturally in collisional rings when stars are redistributed by the shock. While most stars follow the outward wave, some remain trapped in intermediate orbits, stretched into lines that appear as radial features. Gas clouds caught in the same process may fragment and collapse into new clusters, adding small knots of brightness along the filaments. In the cartwheel observations confirm that some of the spoke regions contain young stars, though less intense than those in the outer rim. This indicates that the spokes are not simply empty bridges, but active sites of ongoing processes shaped by the aftermath of collision. The spoke structures also highlight the three-dimensional nature of the disturbance. Although the cartwheel appears nearly face-on from Earth's perspective, its disk has depth, and the collision that created the ring was not perfectly confined to a single plane. As the intruder galaxy passed through it, pulled material not only outward, but also vertically, lifting some stars above or below the disk and creating warped orbits. The spokes may represent the projection of these tilted paths appearing as linear features when viewed against the rest of the disk. This possibility is supported by their uneven thickness and brightness, which suggest overlapping layers of material at different depths. From a dynamical standpoint, the spokes are transitory. They are not stable structures like spiral arms held together by long-lived density waves. Instead, they are remnants of a violent event destined to disperse as orbits continue to evolve. Over time, differential rotation within the galaxy will shear them apart, stretching the filaments into fainter and less distinct patterns. Their presence today is evidence that the collision is still recent, for such features fade within a few 100 million years. This reinforces the conclusion that the cartwheel's transformation took place in the relatively recent past. In addition to stars, the spokes contain dust that absorbs and scatters light. Infrared observations reveal emission from warm dust grains heated by young stars embedded within the filaments. This glow is faint compared with a bright rim, but adds detail to the picture of ongoing star formation. Radio studies also detect traces of gas in these regions, though less abundant than in the ring. The combined evidence suggests that the spokes are not major centers of starburst activity, but secondary sites where residual material continues to collapse and forms stars at a slower rate. The visual impact of the spokes, however, is significant. They break the symmetry of the hollow interior, adding texture and complexity to the otherwise stark contrast between the bright ring and the dim core. Without them, the cartwheel might appear as a simple circle, but with them it becomes a wheel-like structure with radial lines converging toward the center. This geometry is rare among galaxies and contributes to the Cartwheel's distinction as one of the most unusual systems known. For astronomers, the spokes are both a curiosity and a clue offering insight into the detailed mechanics of how a galactic disk responds to sudden disturbance. The formation of the spokes may also involve tidal forces from the companion galaxies. As the Cartwheel's disk was disturbed by the intruder, external pulls from its neighbours may have helped stretch certain regions into filaments. Evidence of tidal debris outside the ring supports this idea, suggesting that material was not only rearranged within the disk, but also drawn outward into intergalactic space. The spokes then may be part of a continuum of features linking the inner regions with the extended tidal streams that surround the system. Observationally, the spokes pose challenges. They are faint and diffuse, requiring sensitive instruments to detect clearly. Earlier images hinted at their presence but lacked resolution to show their full structure. With advances in space-based telescopes and ground-based observatories equipped with adaptive optics, the spokes have been mapped in increasing detail. Their irregular brightness and fragmented appearance have become clearer, showing that they are not smooth lines but rather broken chains of material. Each new observation adds to the understanding of their origin, helping to refine models of collisional ring galaxies. The study of the spokes also informs broader theories of galactic dynamics. In spiral galaxies, arms are understood as density waves that organize star formation into patterns. In the Cartwheel, the spokes represent a different kind of ordering, one born of disruption, rather than sustained waves. They show how galaxies can create temporary patterns under extraordinary conditions, patterns that reveal the hidden mechanics of orbiting matter. By comparing these features with simulations, astronomers can test whether their models capture the full complexity of galactic response to collision. In time, the spokes will fade. The stars within them will continue their orbits, spreading out and blending into the broader disk. The gas will be consumed in star formation or dispersed by stellar winds and supernovae. The dust will be heated and scattered, its infrared glow diminishing as the regions cool. Future observers millions of years from now might see a cartwheel with a bright ring, but no visible spokes, the traces of their existence erased by the steady flow of galactic motion. Yet in the present they remain visible markers of the violent forces that shaped this galaxy, fragile bridges across the gulf between ring and core. For now, the cartwheel retains these radial features as reminders of the passage of an intruder galaxy. They are the lingering scars of the event etched across the face of the system. Though destined to dissolve, they provide valuable information about the immediate aftermath of collision, about how matter is redistributed in both radial and vertical directions, and about how galaxies display transient patterns that reflect the dynamics of their most turbulent episodes. Their fleeting presence underscores the youth of the cartwheel's transformation, and adds one more element of intrigue to this already extraordinary system. Beyond the luminous rim and the faint spokes that span the hollow interior, the Cartwheel Galaxy is surrounded by material that has been flung outward into space. These are the tidal debris fields, sprawling extensions of stars and gas that no longer lie within the ordered boundaries of the disk. Their origin is tied to the violent encounter that reshaped the galaxy. As the intruder passed through, its gravity not only triggered the ring wave, but also drew material outward, stretching and scattering it into long trails. These debris fields now drift at the edges of the system, less concentrated than the ring, but still part of the story of collision. The debris can be subtle when observed in visible light. Stars in these regions are sparse, spread across large volumes of space, and their collective glow is faint. Yet with long exposure imaging, astronomers have traced arcs and streams that extend away from the main disk. These are signs of tidal stripping, where gravitational forces pull stars free from their original orbits and send them onto elongated paths. Some of these stars may eventually fall back toward the galaxy, while others may escape entirely, becoming part of the intergalactic background. The patterns they form give evidence of the direction and scale of the collision. Gas is a significant component of the debris fields. Unlike stars, which move along predictable orbits, gas responds more flexibly to gravitational pulls and collisions. When drawn outward, gas clouds can be stretched into filaments or compressed into knots. Observations in radio wavelengths reveal that the Cartwheel's tidal debris contains reservoirs of neutral hydrogen, the raw material for star formation. In some regions, this gas has cooled and condensed, forming small, faint galaxies known as tidal dwarfs. These objects are not remnants of the original intruder, but new structures assembled from matter torn out of the Cartwheel itself. They represent a form of secondary creation, where the violence of collision leads not only to destruction, but also to the birth of new systems on smaller scales. Infrared observations complement this picture by showing the faint glow of dust carried along with the gas. Dust grains heated by starlight emit at longer wavelengths that can be traced by sensitive detectors. These dusty streams outline where material has been dragged outward and help astronomers understand how far the effects of the collision have reached. The dust is less massive than the stars and gas, but plays a critical role in cooling regions where new stars might form. Its presence in the debris field suggests that the outskirts are not barren, but dynamic zones where material continues to evolve. The morphology of the tidal debris is irregular. Some regions show long curving tails, while others form diffuse envelopes around the galaxy. These differences arise from variations in gravitational forces across the disk during the collision. The intruder's path determined which parts of the Cartwheel were pulled most strongly, and the pre-existing structure of the disk influenced how material responded. Simulations of such events show that different angles of approach can produce very different debris patterns, from symmetric loops to asymmetric streams. The Cartwheel's debris appears to reflect a nearly central collision, but with enough offset to draw out uneven tails. Tidal debris is not unique to the Cartwheel. It is a common feature in interacting galaxies across the universe. Famous examples include the antennae galaxies, where long arcs of stars stretch into space, and the mice galaxies with thin tails extending tens of thousands of light-years. What makes the Cartwheel distinctive is that these debris fields coexist with the ring structure, giving a double record of collision one in the expanding wave across the disk and another in the scattered trails outside it. Together they provide a more complete picture of the forces at work both inward and outward during the encounter. The fate of the tidal debris varies. Some stars in these fields may remain bound to the Cartwheel, orbiting at great distances before slowly falling back. Others moving at higher speeds may escape into intergalactic space, becoming drifters unattached to any galaxy. The gas may form new structures from faint clouds to small galaxies, or may eventually be reabsorbed into the main system. The long timescales of galactic evolution mean that these processes unfold slowly over hundreds of millions of years. Yet even now, observations capture snapshots of the debris in different stages, offering a view of how galaxies exchange material with their surroundings. These debris fields also play a role in enriching intergalactic space. The stars and gas flung outward carry with them heavy elements produced inside the Cartwheel. As they disperse, they seed the environment with these elements, contributing to the gradual enrichment of the cosmic medium. This is part of the cycle of matter, On the largest scales, where collisions and interactions redistribute the building blocks of stars and planets across intergalactic space, the cartwheel, in scattering its material, participates in this ongoing process of exchange between galaxies and their surroundings. Astronomers studying the tidal debris often focus on the balance between stars and gas. Stars provide visible traces, but gas reveals the potential for future evolution. In the cartwheel, the debris fields contain significant amounts of hydrogen, enough to fuel new star formation if conditions allow. Some of the knots observed along the tails show signs of being gravitationally bound, possibly evolving into self-sustaining tidal dwarf galaxies. These would remain as long-term reminders of the collision-independent systems formed from matter once part of the cartwheel's disk. Their survival depends on whether they can hold together against the pull of the larger galaxy and the motions of the group as a whole. The extent of the debris fields also provides information about the energy of the collision. The farther material is thrown, the more forceful the encounter must have been. By mapping the outermost stars and gas, astronomers can estimate the speed of ejection and the gravitational strength of the intruder's passage. These measurements, combined with studies of the ring's expansion, create a consistent narrative of the event: a smaller galaxy plunging through the cartwheel, driving a wave across its disk and scattering material far into space. For observers on Earth, the tidal debris is less immediately striking than the bright ring, but its importance is no less. It is the silent evidence of material displaced the long fingers of a galactic collision stretching into the void. While the ring draws attention with its symmetry and brightness, the debris reveals the asymmetry of the encounter, the parts of the galaxy torn outward rather than compressed inward. Together they form complementary records showing how a single event can shape a system in multiple directions. In time, the debris fields will change. Some of the streams will dissipate as stars drift apart. Others may fall back, merging with the outer regions of the cartwheel. New stars may form in some clumps, while gas in others may disperse into the intergalactic medium. The present state captured in deep observations is only a phase in this long evolution. For now, however, the tidal debris remains, as testimony to the scale of the forces involved, a reminder that galaxies are not closed systems, but participants in dynamic exchanges with their neighbours and their environment. Thus, the cartwheel is not defined solely by its ring or its spokes. It is also surrounded by these extended fields of matter, subtle in brightness but vast in extent. They complete the picture of the collision, showing that the event was not confined to the disk, but reached outward into space, scattering stars and gas into patterns that stretch beyond the visible edge. The debris is part of the galaxy's continuing story, shaping both its future and the environment in which it resides, and ensuring that the signature of the collision is written not only in the ring, but also in the space beyond. Within the rim of the Cartwheel Galaxy, where the density wave moves outward and leaves behind faint spokes and debris, the most vivid transformation unfolds in the regions where gas has been compressed into star-forming complexes. These areas shine with clusters of young stars, their light piercing through the darkness of space, and marking the places where the galaxy is being renewed. The star formation is not uniform. It is concentrated in knots along the ring where the wavefront has pushed interstellar gas into dense clumps that collapse under their own gravity. The result is a burst of activity far stronger than what the cartwheel might have sustained under undisturbed conditions. The process begins when the collision-induced wave sweeps across a section of the disk. Clouds of hydrogen previously diffuse are suddenly compressed. This compression raises density and lowers temperature, enabling the gas to collapse into protostars. Within only a few million years, clusters of massive bright stars ignite their ultraviolet radiation, illuminating the surrounding gas. These regions appear as glowing patches along the ring, bright in visible and ultraviolet light. Observations with space telescopes reveal dozens of such clusters, each containing thousands of stars at different stages of formation. The sheer number and brightness of these knots mark the Cartwheel as a starburst galaxy, one where collision has driven activity far beyond the norm. The scale of this star formation is extraordinary. Some clusters within the Cartwheel rival the most massive star-forming regions known with stellar masses comparable to those of dwarf galaxies. The most massive stars within these clusters burn hot and fast, living only a few million years before ending as supernovae. Their energy shapes the surrounding medium, carving cavities in gas and dispersing dust. This feedback both halts further collapse in some regions and stimulates new collapse in others. The result is a complex cycle of star birth and death playing out across the ring, all set in motion by the initial compression of the collision wave. Infrared observations are crucial to studying these regions, for much of the star formation is hidden by dust. Dust grains absorb visible light, but re-emit it at longer wavelengths, allowing astronomers to trace the hidden populations. In the Cartwheel, infrared surveys reveal that the ring glows brightly with emission, concentrated in the same knots visible in optical light. This confirms that the bright patches are not just surface features, but deep sites of embedded star formation. The dust itself is both a product and a facilitator of this process. Formed in the envelopes of older stars and in supernova remnants, it provides cooling surfaces that allow gas to collapse more efficiently into new stars. Radio observations add another layer of understanding. By mapping the distribution of molecular gas, particularly carbon monoxide, as a tracer, astronomers can measure where the raw fuel for star formation is most abundant. In the Cartwheel, the molecular gas is concentrated in the outer ring, matching the locations of the star-forming complexes. This correlation strengthens the picture of a density wave sweeping outward and piling up gas at the rim. Without the collision, this gas might have remained more evenly spread, sustaining modest star formation across the disk. With the wave, it has been forced into a narrow band where conditions favour rapid and intense collapse. The ages of stars across the Cartwheel provide further evidence of this progression. Spectroscopic studies show that stars in the ring are young with ages of tens of millions of years, while stars in the central regions are older hundreds of millions to billions of years old. This age gradient confirms the outward motion of star formation, with the youngest populations marking the current position of the wave. As the ring continues to expand, new clusters will form farther outward, leaving behind older populations in a layered sequence. In this way, the Cartwheel preserves a temporal record of the collision written in the ages of its stars. The starburst activity also generates high-energy phenomena. The most massive stars quickly evolve into supernovae, releasing vast amounts of energy and creating compact remnants such as neutron stars and black holes. Some of these remnants become powerful X-ray sources as they accrete matter from companion stars. Observations with X-ray telescopes have detected numerous bright sources along the Cartwheel's ring, many associated with young star clusters. These sources highlight the extreme environment of the star-forming complexes, where massive stars are born and die in rapid succession. The impact of this intense star formation is not confined to the clusters themselves. Winds from young stars and explosions from supernovae drive material outward, enriching the surrounding medium with heavy elements. These elements, forged in stellar interiors, are dispersed into gas clouds that may later form new stars and planets. Thus the starburst not only creates light, but also seeds the galaxy with the building blocks of future generations. The Cartwheel's ring is both a nursery and a forge, shaping the chemical composition of the galaxy as it evolves. For astronomers, the Cartwheel offers a unique laboratory to study star formation on galactic scales. Most galaxies form stars in more distributed patterns, making it difficult to isolate the effects of specific triggers. In the Cartwheel, the ring provides a clear boundary where conditions have been set by a known event. By studying clusters at different positions and ages, scientists can test theories of how compression waves influence star formation, how feedback regulates the process, and how starburst activity changes the overall evolution of a galaxy. The Cartwheel is therefore not only a spectacle but also a valuable test case for understanding cosmic processes more broadly. The star-forming complexes also affect the galaxy's appearance across different wavelengths. In visible light, the clusters are bright and blue, dominated by hot young stars. In ultraviolet, they are even more luminous, revealing the energy of their massive members. In infrared, the dust warmed by these stars glows strongly, tracing regions hidden from view in shorter wavelengths. In radio, the molecular gas that fuels the process is mapped in detail. Each band of observation adds depth to the picture, showing how the collision reshaped not only the galaxy's structure, but also its spectrum of light. Over time, the intensity of this activity will wane. As the wavefront continues to move outward, gas in the ring will be consumed or dispersed. Star formation will decline, leaving behind clusters that age and fade. The bright rim will gradually lose its glow, and the Cartwheel will settle into a more quiescent state. But for now, the star-forming complexes mark the galaxy as one of the most spectacular examples of collision-induced activity in the universe, a system where the violent approach of an intruder has been transformed into a burst of creation. The Cartwheel thus illustrates how destruction and creation are intertwined in galactic evolution. The collision tore apart the original spiral structure, scattering material into debris and spokes. Yet it also ignited the birth of thousands of new stars concentrated into clusters that light the rim. This dual outcome, loss of the old order and emergence of the new, is written clearly in the ring's star-forming complexes. They are the most vivid expression of the collision's legacy, turning the galaxy into both a record of past violence and a beacon of present activity. Beyond the blazing knots of star formation that line the Cartwheel's outer ring lies an environment of gas in multiple phases, each responding differently to the shock of collision. This mixture of atomic hydrogen, molecular clouds, and ionized plasma forms the interstellar medium, the material from which stars are born, and into which they release energy when they die. In the Cartwheel, the balance of these components has been profoundly altered. The collision did not merely rearrange the stars, but set off a chain of processes within the gas, shaping the structure and activity of the galaxy in ways that remain visible today. Neutral atomic hydrogen is one of the most abundant components of galactic disks, and in the Cartwheel it stretches far beyond the visible ring. Radio observations at the wavelength of 21 centimeters reveal an extended distribution of hydrogen gas not confined to the bright rim, but spread into the outskirts and debris fields. This shows that the collision disturbed the gas well beyond the region of starburst activity. Some of the hydrogen has been compressed into the ring, where it serves as the raw material for new stars, but much has been scattered outward, forming an envelope around the galaxy. The presence of such a large reservoir suggests that the Cartwheel has fuel to sustain star formation for some time, though its distribution has been radically changed. Molecular gas, the denser phase from which stars form directly, is concentrated in the ring. Observations using carbon monoxide as a tracer show that giant molecular clouds cluster along the wavefront, matching the locations of the luminous star-forming knots. These clouds are colder and denser than atomic gas, shielded by dust and cooled by molecules that radiate away energy. They are highly sensitive to compression, and when the density wave passed through, they collapsed into clusters of new stars. The abundance of molecular gas in the Cartwheel's ring confirms that the collision not only triggered star formation, but also reorganized the gas into a band where such processes are most efficient. Ionized gas, by contrast, reveals the influence of young, massive stars on their environment. Ultraviolet radiation from these stars strips electrons from surrounding hydrogen, creating glowing nebulae known as G regions. In the Cartwheel, these regions are abundant along the ring, forming bright arcs visible in both optical and ultraviolet light. Spectroscopy of these nebulae shows emission lines characteristic of ionized hydrogen-oxygen, and other elements confirming that they are powered by massive stars only a few million years old. The distribution of HI regions traces the current edge of the density wave marking, where the newest clusters have formed. Behind this front, older clusters remain but no longer produce the same intensity of ionization, leaving dimmer remnants. The collision also heated portions of the gas to extreme temperatures, creating a phase observable in X-rays. A supernova exploded within the young clusters. They injected energy into their surroundings, driving shockwaves that heated gas to millions of degrees. Observations with X-ray telescopes revealed diffuse emission across parts of the Cartwheel, particularly near the ring where starburst activity is most intense. This hot plasma is short-lived, as it radiates energy rapidly, but its presence confirms the scale of energetic feedback in the galaxy. The coexistence of hot plasma, warm ionized gas-cold molecular clouds, and extended atomic hydrogen illustrates the full spectrum of interstellar conditions created by the collision. The interaction between these phases is complex. Molecular clouds collapse to form stars which emit radiation that ionizes nearby gas. Massive stars then end their lives as supernovae, dispersing both heavy elements and shock waves that stir the medium. Some regions of molecular gas are destroyed by this feedback, while others are compressed further, creating new cycles of star formation. The Cartwheel's ring is therefore not just a static feature, but a dynamic system where gas phases continually exchange energy and matter. The collision amplified these processes by concentrating gas into the rim, ensuring that interactions occur at higher rates than in a quiescent spiral galaxy. The chemical composition of the gas provides further insight. Spectroscopic measurements show that the ring contains elements heavier than hydrogen and helium, such as oxygen, nitrogen, and sulfur. These elements were produced in earlier generations of stars within the Cartwheel, and expelled into the interstellar medium through winds and supernovae. Their presence in the star-forming regions indicates that the new stars are forming from enriched material, not from pristine gas. This affects the way the gas cools, as metals provide efficient channels for radiation, and it influences the characteristics of the stars that form. By studying these chemical abundances, astronomers can trace how the Cartwheel has evolved through cycles of star formation across its history. The gas outside the ring tells another part of the story. In the tidal debris fields, clouds of atomic hydrogen drift along with scattered stars, showing that the collision displaced material into the outer reaches. Some of this gas may never return, becoming part of the intergalactic medium. Other parts may fall back, potentially fueling future star formation in the Cartwheel or its companions. The distribution of this gas helps astronomers reconstruct the path of the intruder and the scale of the disturbance. It also highlights the role of galactic collisions in redistributing matter on group scales, spreading gas across regions far larger than a single galaxy. Dust, though only a minor fraction of the mass, plays a vital role in the interstellar medium. In the Cartwheel, dust is abundant along the ring where it both obscures and enables star formation. In visible light, dust lanes appear as dark streaks that absorb starlight, reducing brightness in some regions. In infrared, the same dust glows as it absorbs energy from nearby stars. Observations at these wavelengths show that the Cartwheel's ring is rich in warm dust, heated by the massive clusters that have recently formed. This dust is crucial for the cooling of gas, allowing molecular clouds to collapse, but it also complicates observation, hiding young stars behind thick curtains. The interplay between dust and gas defines much of the galaxy's appearance and activity. The interstellar medium in the Cartwheel is therefore a layered and dynamic environment, reshaped by the collision, and now fueling one of the most intense episodes of star formation known in such systems. Each phase of the gas tells part of the story. Atomic hydrogen marks the extended reach of the disturbance. Molecular gas reveals where stars are forming ionized gas, highlights the youngest regions, and hot plasma traces the energy of stellar death. Dust ties these components together, both obscuring and enabling the processes at work. Together they create a portrait of a galaxy in flux, its gas driven into new arrangements by the passage of a smaller companion. Over time, the balance of these gas phases will change. Molecular clouds will be consumed or destroyed, reducing star formation rates. Ionized regions will fade as massive stars die. Hot plasma will cool, while atomic hydrogen may either settle back into the disk or disperse outward. The Cartwheel will gradually evolve from its current starburst phase toward a quieter state. Yet for now, its gas remains in turmoil, shaped by the collision into structures that glow across the electromagnetic spectrum. The study of this medium provides not only a window into the Cartwheel's present, but also a glimpse of how galaxies respond to the most dramatic of encounters. Amid the disrupted gas and dust of the Cartwheel Galaxy, one component plays a particularly revealing role: the dust lanes and the infrared emission that traces their presence. Dust is only a small fraction of the total mass of a galaxy, but it governs much of what astronomers see and much of how gas evolves into stars. In the Cartwheel, the collision has rearranged dust just as it did gas, concentrating it in the outer ring, while leaving streaks and filaments across the interior. When observed in visible light, these dust lanes appear as dark, irregular features that cut across brighter regions, absorbing and scattering starlight. But in infrared wavelengths, the same dust glows, warmed by the energy of nearby stars, and outlines the hidden processes of star formation across the galaxy. The dust lanes are most striking along the rim, where young clusters illuminate them from within. Here dense clouds of gas and dust lie just behind the advancing density wave, catching the light of newborn stars and glowing in infrared. These lanes are not smooth bands, but complex networks twisted by turbulence and feedback. Winds from massive stars carve holes and bubbles, while supernovae blast cavities that disperse material. The result is a patchwork of dusty regions, some dark against the stars, others shining brightly at longer wavelengths. Observations reveal that the outer ring of the Cartwheel is not simply a band of stars, but a layered structure of gas dust and young clusters intertwined. In the interior, the dust lanes are fainter but still present. They trace the remnants of the original spiral arms distorted by the collision. Some lanes stretch inward toward the central core, appearing as faint streaks that cut across the hollow space. These features may mark where material were drawn toward the center during the passage of the intruder galaxy, then left behind as the wave moved outward. Their irregularity contrasts with the ordered dust lanes of an undisturbed spiral, emphasizing the chaotic aftermath of collision. Yet even here, dust continues to shape the interstellar medium, cooling gas and providing sites for molecules to form. Infrared surveys have been particularly valuable for mapping the Cartwheel's dust. Instruments sensitive to mid and far infrared light detect emission from grains at different temperatures. Warm dust heated by nearby young stars radiates strongly at shorter infrared wavelengths, highlighting active star-forming regions. Cooler dust farther from stellar heat glows at longer wavelengths, tracing the diffuse material spread across the ring and debris fields. In the Cartwheel, both components are prominent, showing that dust is abundant not only in the clusters, but throughout the disturbed disk. The overall brightness of the galaxy in infrared marks it as a starburst system, one where dust reprocesses much of the starlight into longer wavelengths. The role of dust extends beyond observation. It directly influences the physics of star formation. By absorbing radiation and cooling gas dust, allows molecular clouds to collapse more efficiently. In the Cartwheel, this function is critical for the collision-piled gas and dust into dense lanes, where collapse became inevitable. Without dust, the gas might have resisted compression, but with dust present, cooling was rapid and star formation ignited on massive scales. The infrared glow of the Cartwheel is therefore not only a tracer of young stars, but also evidence of the enabling role dust played in their creation. The chemical composition of the dust adds another layer of information. Dust grains are formed from heavier elements such as carbon, oxygen, silicon, and iron produced in earlier generations of stars. Their abundance in the Cartwheel indicates that the galaxy has undergone multiple cycles of star formation across its history, enriching the interstellar medium with metals. The collision did not create this dust but redistributed it, concentrating it in new configurations. This enrichment means that the stars forming today in the ring are born from material already seeded with elements necessary for planets and complex chemistry. Thus, the dust lanes of the Cartwheel connect the galaxy's violent present with its long evolutionary past. Comparisons across wavelengths show how dust obscures as well as reveals. In optical light, the bright rim of the Cartwheel is patchy with dark gaps where dust lanes block starlight. In infrared, these same regions shine filled with emission from heated grains. This dual role complicates direct observation of young stars, for many are hidden behind thick curtains of dust. Yet it also provides astronomers with tools to measure the total star formation rate. By combining optical and infrared data, scientists can estimate how much starlight is absorbed and re-emitted, ensuring that hidden clusters are not overlooked. In the Cartwheel, such measurements confirm that the galaxy is forming stars at a rate far higher than ordinary spirals of similar size. Dust lanes also provide clues to the galaxy's three-dimensional structure. Their orientation and thickness reveal how the disk has been warped by the collision. Some lanes appear tilted, suggesting that parts of the disk were lifted above or below the main plane. Others are twisted, indicating shear forces at work. These distortions match simulations of collisional rings, where the passage of an intruder sets off vertical, as well as radial motions. The dust by tracing where gas and stars have moved records the complex dynamics of the encounter, in ways visible even millions of years later. Outside the ring, dust is more diffuse but still present. Infrared maps show faint emission in the tidal debris fields carried along with the gas pulled outward during the collision. This dust is less concentrated and cooler, but its detection proves that the effects of the collision reached far beyond the visible disk. Some of this dust may eventually disperse into intergalactic space, joining the broader medium between galaxies. In this way, the Cartwheel contributes not only stars and gas, but also dust to its environment, enriching the cosmic background with the products of stellar evolution. For astronomers, the study of dust and infrared emission in the Cartwheel is part of a broader effort to understand how galaxies process and recycle matter. Dust is both a byproduct of stellar death and a catalyst for new birth. Its presence in such abundance within the Cartwheel underscores the efficiency of these cycles even amid disruption. By observing the galaxy at multiple wavelengths, scientists can piece together a more complete picture, one where visible light shows the stars, radio reveals the gas, and infrared uncovers the hidden interplay of dust and star formation. Over time, the dust lanes of the Cartwheel will evolve. Some will be consumed as gas collapses into stars, while others will be dispersed by winds and supernovae. The bright infrared glow will fade as star formation slows, leaving behind older stars that emit less energy. Yet for now, the dust ensures that the Cartwheel remains one of the most luminous infrared galaxies of its type, a system where collision has turned ordinary interstellar matter into a brilliant display across the spectrum. The dust lanes, intricate and ever-changing, are both evidence of past enrichment and engines of present creation, making them central to the ongoing transformation of this remarkable galaxy. Between the blazing outer ring and the compact core of the Cartwheel Galaxy lies an intermediate disk populated by older stars, lingering gas, and remnants of structures that predate the collision. This region, overshadowed by the brightness of the rim, offers a quieter but no less important record of the galaxy's history. Here, astronomers find the populations that bridge the past and present stars formed before the intruder's passage, stars created in the earlier stages of the outward-moving wave, and stars now caught in disrupted orbits that no longer resemble the orderly spirals of an undisturbed disk. The light from this intermediate zone is dominated by older, redder stars. These are stellar populations with ages measured in hundreds of millions to billions of years, survivors from the time before the collision. They once likely arranged themselves in spiral arms similar to those seen in the Cartwheel's neighbouring galaxies, tracing density waves across the disk. But the impact scrambled these patterns, redistributing stars into more irregular configurations. When astronomers map this light, they find that the inner disk appears less structured, with patches of starlight scattered across, rather than ordered into clear arms. This is consistent with simulations that show how a head-on collision disrupts existing spiral density waves, leaving behind remnants that slowly shear apart. Superimposed on this older background are younger populations formed as the ring wave swept through. These stars, though less numerous than those in the outer rim, still contribute significantly to the light. They tend to cluster in arcs or fragments, marking the positions where the wavefront passed tens to hundreds of millions of years ago. Their distribution provides a record of the wave's progression, showing that the ring we see today once occupied smaller radii. By comparing the ages of these stars with the current size of the ring, astronomers confirm the outward speed of the wave and refine estimates of when the collision occurred. The gas content of the intermediate disk is lower than in the outer rim, but not absent. Pockets of atomic hydrogen and residual molecular clouds remain, though many have been consumed or dispersed by previous star formation. These pockets contribute to faint, scattered regions of ongoing activity, visible in both optical and infrared observations. Compared with the luminous knots of the outer ring, these regions are modest, forming fewer stars and producing less intense emission. They mark the remnants of earlier bursts now fading as the wave continues outward. Their presence shows that the Cartwheel's transformation is not confined to a single ring, but involves a continuous trail of activity left behind as the wave expands. The stellar populations of the intermediate disk also provide crucial information about the galaxy's chemical history. Spectroscopic studies of these stars show that they are more chemically enriched than those in the outer ring, containing higher proportions of heavy elements. This is expected as they formed earlier from gas that had already undergone multiple cycles of enrichment through stellar evolution. By contrast, stars in the outer ring, though also enriched, represent younger generations with somewhat lower metallicity. The gradient in chemical composition from inner to outer regions is an important diagnostic, revealing how the cartwheel has processed its material across time. It also confirms that the collision did not erase the chemical record but merely overlaid it with new generations of stars. The dynamics of the intermediate disk reflect the disturbance caused by the intruder. Instead of smooth circular rotation, stars here show signs of irregular motion, with velocities shifted by the passing wave. Some stars lag behind the expanding front, while others have been pulled into elongated orbits that distort the overall pattern. These irregularities contribute to the sheared appearance of the region, where light is patchy and diffuse, rather than neatly aligned. Over time, gravitational interactions may smooth out these irregularities, but for now they remain visible as evidence of the turbulence introduced by collision. Observations in different wavelengths highlight additional details of this region. In ultraviolet light, faint emission marks older star-forming regions now dominated by intermediate-age stars rather than newborn clusters. In infrared, diffuse glow reveals residual dust warmed by lingering stellar populations. In X-rays, occasional sources indicate the presence of compact remnants left behind by massive stars that formed earlier in the wave's passage. Together, these data portray the intermediate disk as a transitional zone quieter than the rim, but still shaped by the same event, containing relics of both past and present phases of activity. The contrast between this intermediate zone and the outer ring underscores the dynamic nature of the cartwheel's evolution. In the ring, star formation is vigorous, gas is abundant, and light is dominated by young blue stars. In the intermediate disk, star formation has largely subsided, gas is depleted, and light is dominated by older, redder populations. This gradient reflects the outward progression of the density wave, with each region representing a different stage of the process. By studying these differences, astronomers can reconstruct the timeline of events with remarkable precision, linking stellar ages, chemical abundances, and spatial distribution into a coherent history. The intermediate disk also raises questions about the future of the cartwheel. As the outer ring continues to expand, the stars left behind will age and fade, leaving a growing gap between the rim and the core. This hollowed structure may persist for hundreds of millions of years, creating a system that looks increasingly like a ring surrounding a sparse interior. Whether the intermediate stars will eventually settle into new patterns or remain in diffuse distributions is uncertain, but their current state suggests that the cartwheel will not easily return to its original spiral form. Instead, it is on a path toward becoming a system with distinct outer and inner regions shaped by the legacy of collision. For astronomers, the intermediate disk is valuable because it provides a natural laboratory for studying stellar populations at different stages of disruption. Unlike the outer ring, where activity is intense and ongoing, or the central core, where much has been stripped away, this region preserves a mix of elements. It contains stars from before the collision stars formed during earlier phases of the wave, and residual gas that marks the transition between phases. By analyzing these components, scientists can test models of how galaxies respond to collisions not just at their edges, but throughout their disks. Thus, the intermediate populations of the cartwheel are more than background light between ring and core. They are the bridge between eras, linking the galaxy's spiral past with its ring-shaped present. Their disrupted orbits, varied ages, and chemical signatures hold the record of how the density wave reshaped the disk, leaving behind a stratified system of stars that narrates the timeline of collision. In their scattered light, astronomers read the middle chapters of the cartwheel's story, chapters that might otherwise be hidden by the brilliance of the ring or the emptiness of the core. but which are essential to understanding the galaxy as a whole. Within the Cartwheel Galaxy, the passage of the intruder not only rearranged stars and gas into rings and spokes, but also created conditions for extreme stellar evolution. The intense bursts of star formation along the rim have produced many massive stars, each destined to live fast and die violently. These short-lived giants end their lives as supernovae, scattering heavy elements into their surroundings and leaving behind compact remnants such as neutron stars and black holes. The result is a galaxy that shines not only in visible and infrared light, but also in high-energy wavelengths where supernova remnants and X-ray sources mark the aftermath of stellar death. The evidence for supernovae in the Cartwheel is abundant. The bright knots of young clusters along the outer ring contain stars many times the mass of the Sun, burning hot and exhausting their fuel in only a few million years. Since the collision occurred a few 100 million years ago, many waves of these stars have already lived and died, each generation enriching the galaxy with heavy elements. Observations reveal expanding shells of gas around certain regions, the telltale signatures of supernova explosions. These shells glow in optical emission lines such as hydrogen alpha, in radio waves from accelerated electrons, and in X-rays from the shock-heated plasma. Together they confirm that the Cartwheel is a galaxy alive with stellar death as much as stellar birth. X-ray telescopes have uncovered numerous bright sources along the ring, many of them ultraluminous compared with typical X-ray binaries in the Milky Way. These sources are thought to be compact remnants, neutron stars, or black holes accreting matter from companion stars. In the dense star-forming environments of the Cartwheel, such systems are common. Massive stars often form in binaries, and when one collapses into a compact object, it can draw gas from its partner, emitting powerful X-rays as the material falls inward. The abundance of these sources in the Cartwheel reflects the galaxy's recent starburst activity and highlights the extreme conditions produced by collision. In addition to individual remnants diffuse, X-ray emission pervades parts of the galaxy, particularly the outer ring. This emission arises from gas heated to millions of degrees by the combined effects of stellar winds and supernova explosions. Such hot plasma expands into surrounding space, creating bubbles and cavities that further shape the interstellar medium. In the Cartwheel, this diffuse glow is evidence of the energy injected by thousands of massive stars over the last few 100 million years. It confirms that the galaxy is not only forming stars at high rates, but also experiencing high rates of stellar death, and feedback, a cycle that continuously reshapes the environment. Radio observations add further detail by detecting synchrotron radiation from electrons accelerated in supernova shocks. These signals trace the expanding remnants of past explosions, marking regions where massive stars once lived. The distribution of this emission along the ring parallels the distribution of star-forming complexes, reinforcing the view that the Cartwheel's rim is both a cradle and a grave for stars. Each supernova remnant adds to the chemical enrichment of the galaxy, scattering elements such as oxygen, silicon, and iron into the interstellar medium. These elements cool the gas-formed dust grains and seed the next generations of stars, continuing the cycle of matter across cosmic time. The interplay between supernova remnants and their surroundings is especially dramatic in the Cartwheel because of the density of the ring. In less active galaxies, supernovae may explode into relatively diffuse environments, dispersing quickly. In the Cartwheel, they occur within compressed gas and dust, where their shockwaves interact strongly with surrounding material. This can trigger further star formation by compressing nearby clouds, or can disperse gas and halt formation in some regions. The balance between these effects determines how efficiently the galaxy converts its gas into stars. Observations suggest that in the Cartwheel, the overall effect has been to sustain the starburst as feedback compresses some regions even while dispersing others. The high-energy environment also produces rare phenomena such as ultra-luminous X-ray sources, which may involve black holes larger than those formed by single stars but smaller than the supermassive black holes at galactic centers. The Cartwheel hosts several candidates for such objects, though their true nature remains debated. They may be stellar mass black holes accreting at unusually high rates, or intermediate mass black holes formed through unusual processes. Whatever their origin, their presence underscores the extraordinary conditions in the Cartwheel's ring, where the aftermath of collision has created an environment conducive to exotic stellar remnants. The importance of these high-energy sources extends beyond the Cartwheel itself. By studying them, astronomers gain insight into how starbursts in other galaxies might produce compact object populations, how feedback shapes galactic evolution, and how collisions influence the life cycle of stars on large scales. The Cartwheel is valuable precisely because it provides a clear timeline. The collision triggered the starburst produced massive stars, and those stars quickly evolved into supernovae and remnants. This sequence allows scientists to connect cause and effect in ways not always possible in more complex systems. The visual impression of the Cartwheel with its bright rim and dark center is thus only part of its reality. Beneath the optical image lies a galaxy alive with high-energy processes invisible to the naked eye, but revealed through specialized instruments. X-rays trace the hot gas and compact remnants. Radio waves trace the expanding shells of supernovae, and optical spectra trace the emission from ionized gas. Each wavelength tells part of the story of how massive stars are born live and die in the wake of collision. Together they reveal a galaxy where the cycle of creation and destruction is amplified to extraordinary levels. The supernova and their remnants also contribute to the shaping of the Cartwheel's structure. By driving gas outward, they may help maintain the ring's sharp edge, clearing material from behind the wavefront and concentrating it along the rim. They also stir turbulence within the gas, preventing it from settling into calm patterns. In this way, stellar death reinforces the structural consequences of collision, sustaining the galaxy's unusual form. The Cartwheel is not simply passively evolving after impact, but actively maintained in a state of turmoil by the energy of its youngest and most massive stars. Over time, the population of massive stars will decline as gas is consumed and the starburst subsides. The number of new supernovae will decrease, the X-ray sources will fade, and the diffuse hot plasma will cool. Yet for now, the Cartwheel remains a galaxy, where stellar death is as conspicuous as stellar birth, where the ring is not only a nursery of stars but also a cemetery of giants. Its high-energy phenomena are integral to its identity, marking it as a system transformed not only in structure but in the very life cycle of its stars. Thus the Cartwheel demonstrates how a galactic collision can accelerate every stage of stellar evolution, from the collapse of clouds into clusters to the violent explosions that end the lives of massive stars. The remnants of these explosions, visible across the electromagnetic spectrum, ensure that the record of this process is clear. They are the echoes of the collision, as vital to the story as the ring and spokes. By tracing them, astronomers read the consequences of galactic impact not only in visible light, but in the high-energy glow of a galaxy still reverberating with the deaths of stars. Closer to the center of the Cartwheel Galaxy, inside the fading brightness of the intermediate disk, the effects of the collision are recorded in the motion of stars and gas. Unlike the sharply defined rim which shows the clear front of the expanding wave, the inner disk is a zone of turbulence and shear where rotation is no longer smooth and ordered. Before the passage of the intruder, The cartwheel likely resembled its spiral neighbours, with stars orbiting in nearly circular paths around the galactic centre. The collision disrupted that symmetry. Gravitational forces from the intruder pulled some material inward and pushed other material outward, setting stars onto new orbits that cross and twist. Today, the inner disk reveals this disruption, as irregular flows disturbed velocities and evidence of differential motion that betrays the system's scar. Spectroscopic studies provide direct evidence of this disturbed kinematics. By measuring the Doppler shifts of light from gas and stars, astronomers can determine how material is moving toward or away from Earth. In an undisturbed spiral, these measurements trace a smooth rotation curve. One side of the galaxy moves slightly toward us, the other slightly away as the whole disk spins around the centre. In the cartwheel, this pattern is broken. Velocities are irregular, with patches of gas moving at unexpected speeds or directions. Some regions show signs of inflow material being drawn toward the centre, while others reveal outflow gas pushed outward by the collision. The overall effect is a shear pattern, where different layers of the disk move past one another instead of rotating in harmony. These motions are not random but consequences of the physics of impact. When the intruder plunged through, it introduced a gravitational disturbance that propagated through the disk like a ripple. In the outer regions, this ripple is visible as the ring. In the inner regions, the effect was less orderly. Material closer to the centre experienced strong gravitational compression, followed by release, leaving behind oscillations and non-circular motions. The result is turbulence visible in the irregular distribution of gas and the sheared paths of stars. Over time, these motions may settle, but for now they preserve evidence of the recent collision. Gas in the inner disk shows particular signs of disruption. Spectroscopy reveals broadened emission lines indicating turbulence and high-velocity dispersion. Instead of moving in narrow, well-defined streams, the gas is stirred into chaotic flows. Some of this motion arises from feedback by young stars and supernovae, but much of it originates from the collision itself. Radio maps of hydrogen show that gas density is patchy and uneven, with holes and clumps rather than smooth distributions. These irregularities correspond to the disturbed kinematic, showing that gas has been pulled into complex flows that defy simple rotation. Stars, being less responsive to pressure, preserve different signatures. Their motions are more stable, but many have been shifted into elongated orbits crossing paths that once were nearly circular. As these orbits intersect, the stellar distribution becomes less symmetric. The inner disk of the cartwheel thus lacks the graceful spirals of its neighbours and instead displays diffuse irregular light. This irregularity is reinforced by the presence of spokes, which connect the rim to the core and intersect the inner disk. These radial features further distort the appearance of rotation, making the centre appear chaotic compared with the ordered patterns of a normal spiral. Despite this turbulence, some coherence remains. On large scales, the inner disk still rotates around the central region, and the overall sense of motion is not lost. The gravitational pull of the galaxy ensures that stars and gas remain bound even if their paths are irregular. Over hundreds of millions of years, dynamical friction and differential rotation may restore more order, smoothing out the sheared motions into a new equilibrium. But for now, the cartwheel is caught in transition with its inner disk, showing the unsettled flow of a galaxy still reverberating from impact. The shear in the inner disk also affects star formation. While the outer rim is dominated by intense bursts, the centre shows relatively little new activity. One reason is that turbulence prevents gas from collapsing easily. Clouds are stirred and dispersed, unable to cool and condense into stars. Another reason is that much of the gas was swept outward into the rim, leaving the inner regions depleted. The result is a central zone dominated by older stars with few young clusters to replenish its light. This contrast with the brilliant rim emphasizes the uneven distribution of activity created by the collision. Multi-wavelength observations highlight the contrast between turbulence and quiet. In optical light, the inner disk glows faintly, its stars older and redder. In infrared, some residual dust emission is visible but far weaker than in the rim. In ultraviolet, the center is almost dark, confirming the lack of recent star formation. In X-rays, however, there are still isolated sources, remnants of past supernovae and binaries left over from earlier waves of activity. These high-energy signals reveal that the center is not completely dormant, but carries the echoes of activity from previous generations of stars. The disturbed motions also provide clues to the mass distribution within the galaxy. By mapping the velocities of stars and gas, astronomers can infer the underlying gravitational potential. In the Cartwheel, these measurements suggest that dark matter, as in other galaxies, dominates the mass but is now masked by turbulence. The collision disrupted the visible disk, but the dark matter halo remains intact, anchoring the system and guiding its long-term evolution. This combination of disruption in the baryonic matter and stability in the dark halo is key to understanding why the Cartwheel remains coherent despite the violence of its history. For astronomers, the inner disk is important because it demonstrates how collisions affect galaxies on scales smaller than the outer ring. While the ring provides a dramatic record of the wavefront, the inner regions show how turbulence and shear reshape the dynamics closer to the core. By studying these motions, scientists can refine models of collisional rings, ensuring that they capture not only the visible structures, but also the hidden kinematics beneath. The Cartwheel, with its proximity and clarity, provides a test case for these models, offering insights that can be applied to more distant systems. Over time, the shear in the inner disk may fade as irregular orbits are smoothed by gravity. Gas may settle into new patterns, perhaps forming a more ordered disk around the core. But for now, the Cartwheel preserves this transitional state with its inner regions reflecting the scars of collision. The turbulence, the broadened emission lines, the irregular orbits, all are part of the record of an event that transformed the galaxy. They remind us that galaxies are not static structures, but dynamic systems shaped by encounters and restored only slowly to equilibrium. Thus, the inner disk of the Cartwheel is a region of unsettled flows, a scar left by the intruder's passage. It is quieter than the rim, but no less important, for it holds the evidence of disruption in motion and structure. In its turbulence, astronomers read the story of how the galaxy responds not just at its edges, but at its core, where the pull of gravity and the chaos of collision meet. The Cartwheel's unusual form is not only visible in its bright ring, but also written in the shear and irregularities of its inner disk, a record of disturbance preserved in the motions of stars and gas. Near the heart of the Cartwheel Galaxy, inside the radius of the disrupted inner disk, faint traces of ordered structure still remain. Among these are the remnants of a central bar or inner disk formations that survived the collision, though in weakened and distorted form. In many spiral galaxies, bars are elongated structures of stars and gas that channel material inward, fueling central activity and shaping the overall dynamics of the disk. Before the collision, the Cartwheel may have possessed such a bar as its neighbouring galaxies do. After the passage of the intruder, however, the bar was left altered, its clarity diminished by the wave that reorganized the surrounding disk into the bright outer ring. What remains today are hints of symmetry near the center, mixed with turbulence and irregular orbits that testify to both persistence and disruption. High-resolution imaging shows faint elongations of light in the central region, not aligned with the outer ring but stretching across the inner disk. These features are interpreted as possible bar remnants, distorted by the collision, but still visible against the background of older stars. Unlike the luminous clusters of the rim, these stars are redder and older, representing populations formed long before the event. Their presence confirms that the Cartwheel did not lose all of its inner structure, but retained fragments of what was once a more typical spiral configuration. These bar-like features are faint, however, and difficult to distinguish from the irregular flows of the inner disk, suggesting that the collision weakened their prominence. Spectroscopic studies of stellar motion lend further support to the presence of residual structure. Stars in the central region show velocity patterns that suggest elongation, with orbits stretched along a preferred axis rather than perfectly circular. Such motion is consistent with bar dynamics, where gravitational instabilities create elongated paths that align into a collective feature. Yet these patterns are irregular and partially broken, reflecting the turbulence introduced by the intruder's passage. The Cartwheel thus appears to have a bar remnant that has survived in diminished form, providing a glimpse of the galaxy's pre-collision state amid its transformed appearance. Gas flows in the central regions also hint at bar-like behavior. In barred spirals, gas is often funneled inward along the bar-feeding central star formation or activity around a black hole. In the Cartwheel, some residual inflow is seen, though weaker than in intact barred galaxies. The turbulence of the inner disk and the depletion of gas toward the centre have reduced the bar's ability to concentrate material. As a result, the core shows relatively little star formation compared with the outer ring. This contrast emphasizes how the collision shifted activity outward, stripping the bar of its usual role in fueling central processes. The remnants of inner structure are not limited to the bar. Astronomers also observe arcs and loops of stars within the core features that may represent the fragments of spiral arms disrupted by the collision. These arcs, though faint, provide further evidence that the Cartwheel once resembled a more ordinary spiral before it was struck. Together with a possible bar remnant, they paint a picture of a galaxy that retained parts of its inner geometry, even as its outer regions were dramatically transformed. The collision did not erase all memory of its former self, but left behind vestiges that survive amid the scars. The persistence of such features illustrates the resilience of galactic structure. While the outer disk was reorganized into a ring, and the inner disk was thrown into turbulence, the very core retained enough gravitational stability to preserve traces of order. This suggests that while the intruder's passage was catastrophic for the disk as a whole, its effects diminished toward the center, where the gravitational potential is steepest. Stars near the core remained more tightly bound, less susceptible to being flung outward, and so they held on to partial coherence. What remains today is not an intact bar or spiral, but the faint shadow of one recognizable through careful observation. The presence of residual inner structure also informs theories of how ring galaxies evolve. Models suggest that over time, as the ring expands and fades, the inner regions may reassert themselves with bars and spiral patterns reforming from the surviving populations. In the Cartwheel, this process may already be underway as the bar remnant continues to influence motions in the core. If gas later falls back into the center, new star formation could revive these patterns, gradually restoring more ordered structures. For now, however, the balance remains tilted toward disruption, with turbulence still dominant in the inner disk. Infrared observations add further depth to this picture. While visible light emphasizes the bright rim, and Spoke's infrared imaging reveals the distribution of older stars in the center, highlighting the faint elongations of the possible bar. These populations dominate the mass of the galaxy, even if they contribute less to its visible brightness. By mapping their distribution, astronomers can reconstruct the pre-collision structure more clearly inferring that the cartwheel once resembled a barred spiral similar to its companions. This reinforces the idea that the galaxy we see today is not a fundamentally different kind of system, but a spiral transformed by a singular event. The remnants of inner structures also constrain the identity of the intruder. Simulations of collisional rings show that the degree to which central bars and inner arms survive depends on the angle, speed, and mass of the passing galaxy. In the cartwheel, the survival of faint bar-like features suggests that the collision was near central, but not perfectly aligned, powerful enough to generate the outer ring, but not to erase all inner order. By matching models to observation, astronomers can refine estimates of the intruder's trajectory and mass, narrowing the parameters of the event that reshaped the system. Over cosmic timescales, the fate of these inner remnants is uncertain. They may fade further as the galaxy continues to evolve, blending into the diffuse background of old stars, or they may regain prominence if gas returns to the center and fuels new activity. Either way, their current presence provides an essential link between the cartwheel's past and present. They are the surviving signatures of the galaxy's spiral origin, visible even amid the extraordinary transformation that defines it today. Thus, at the core of the cartwheel lies not emptiness, but a faint record of resilience, bar-like elongations, arcs of disrupted arms and motions that preserve echoes of ordered structure. They are subtle compared with the bright rim, yet they are crucial for understanding the galaxy's evolution. They remind us that even in the aftermath of violent encounters, parts of a galaxy can endure, preserving the memory of what came before. In the cartwheel, these inner remnants connect the present spectacle of the ring with the quieter spiral system it once was, offering a glimpse of continuity amid change. At the very nucleus of the Cartwheel Galaxy, deeper than the disrupted disk and faint bar remnants, lies a compact region that holds the gravitational anchor of the entire system. This nucleus, though dim compared with the blazing outer rim, is central to the galaxy's stability. It contains the densest concentrations of stars remnants of the original spiral core, and possibly a central black hole whose activity has been muted by the effects of collision. Studying this region is challenging, as much of the galaxy's gas and dust was swept outward during the passage of the intruder, leaving the core relatively starved of the raw material that would otherwise fuel central brightness. Yet even in its subdued state, the nucleus carries important clues about the cartwheel's inner life and long-term fate. The light from the nucleus is dominated by older stellar populations. These stars are redder and less luminous than the hot blue stars of the outer rim, but they represent the accumulated mass of billions of years of star formation prior to the collision. Their density near the center creates the gravitational well that binds the rest of the galaxy. When astronomers measure the motions of stars near the nucleus, they find velocities consistent with the presence of a concentrated mass, a hallmark of galactic centers. Yet unlike many other galaxies of similar size, the Cartwheel shows little evidence of intense nuclear activity, suggesting that the central black hole, if present, is currently quiescent. The question of a central black hole is particularly intriguing. Most galaxies of the Cartwheel's scale are thought to harbour supermassive black holes with masses millions to billions of times that of the Sun. In active galaxies, these objects reveal themselves through bright emission, as gas falls inward, releasing energy across the electromagnetic spectrum. In the Cartwheel, however, such signatures are faint or absent. X-ray and radio surveys detect only weak sources near the centre, consistent with low levels of accretion. This suggests that the collision may have deprived the black hole of fuel by sweeping gas outward into the rim. Without a steady flow of matter, the nucleus remains quiet, its central object concealed within the starlight. Spectroscopic studies confirm that the nucleus is chemically enriched, containing stars with higher metallicities than those in the outer regions. This reflects its history as the site of earlier star formation, where multiple generations of stars enriched the gas before forming new ones. These populations provide a fossil record of the Cartwheel's long evolution prior to the collision, when it likely resembled a more typical spiral galaxy. The contrast between the enriched nucleus and the younger, less enriched populations of the ring highlights the layered history of the system, with the core representing the old and stable, while the rim represents the young and transient. The dynamics of the nucleus reveal further complexity. While the overall motion is dominated by rotation around the center, irregularities remain introduced by the disturbance of the collision. Some stars show motions not aligned with the main axis, suggesting that their orbits were perturbed during the intruder's passage. Gas motions are even more irregular, with weak signs of inflow along possible bar remnants, but little evidence of coherent streams. The turbulence of the inner disk appears to extend inward, blurring the sharpness of nuclear dynamics. Yet the gravitational potential of the core ensures that these motions remain bound, preventing complete disruption. Infrared imaging has revealed concentrations of dust even within the nucleus, though far less abundant than in the ring. This dust glows faintly, heated by the surrounding older stars. It may represent the remnants of material that once fueled central star formation but was largely stripped away. Without fresh gas, the nucleus produces few new stars and its luminosity declines compared with the active rim. This depletion underscores how the collision redistributed material, concentrating it outward and leaving the center barren. In effect, the Cartwheel's star-forming heart was displaced to the edge, while its nucleus entered a phase of quiet endurance. The possible presence of a central black hole, even if dormant, remains significant. Its mass can be estimated indirectly by measuring stellar velocities near the center, though such measurements are challenging at the Cartwheel's distance. Preliminary estimates suggest that if a supermassive black hole exists, it is consistent with expectations for a galaxy of this mass. The absence of strong nuclear activity does not rule it out. Rather, it indicates that conditions are not currently favorable for accretion. This quiescence is not unusual, as many galaxies harbor black holes that are active only intermittently depending on the supply of gas. The Cartwheel's quiet nucleus may therefore be a temporary state, one that could change if gas later falls back inward. The nucleus also provides a reference point for the galaxy's chemical and dynamical gradients. By comparing metallicities, stellar ages, and velocities from the center outward, astronomers can trace how the collision altered the distribution of matter. The Cartwheel shows steep contrasts, enriched and old at the core, young and moderately enriched at the rim, disrupted and mixed in between. These contrasts map the journey of gas and stars across time and space, recording both the pre-collision history and the aftermath of impact. Without the nucleus as a stable anchor, this record would be incomplete. Although the Cartwheel's nucleus is subdued, it is not inert. Occasional compact X-ray sources within the central region may represent binaries or remnants of past stellar evolution. These sources are far less numerous than those in the rim, but they confirm that high-energy processes continue even here. Radio observations also detect faint emission, possibly linked to supernova remnants from earlier starburst phases or to weak activity around the central black hole. These signals are faint but important, as they provide evidence of continued though reduced energy release in the heart of the galaxy. Over the long term, the fate of the nucleus may depend on how material redistributes. If gas from the outer ring eventually drifts inward, the nucleus could experience renewed star formation or even ignite active galactic nucleus activity. If not, it will remain dominated by its older stellar populations slowly fading as stars age and die. Either way, it will continue to serve as the gravitational center, the point around which all other structures orbit. Its quiet persistence contrasts with the brilliance of the ring, reminding astronomers that galaxies can contain both extremes of activity within the same system. Thus, the nucleus of the Cartwheel is not the most striking part of the galaxy, but it is essential to its structure and story. It represents the old core of a spiral galaxy that survived a collision now stripped of much of its gas and hidden beneath the spectacle of the outer ring. It may harbour a dormant supermassive black hole, a silent anchor of gravity awaiting future fuel. Its stellar populations preserve the chemical memory of the past, while its dynamics reveal the scars of disturbance. Though less dramatic in appearance, the nucleus completes the picture of the Cartwheel, grounding the galaxy's transformation in a quiet but enduring core. The chemical fingerprints across the Cartwheel Galaxy reveal a story as important as its visible structures. When astronomers measure the abundances of heavy elements in different regions of the system, they find gradients that trace both its past evolution and the consequences of its violent collision. These metallicity patterns, as they are called, are the distribution of elements heavier than hydrogen and helium that stars have forged and released into the interstellar medium. In an undisturbed spiral galaxy, metallicity generally decreases outward from the core, the center having formed stars longer and at higher rates is enriched, while the outskirts contain less processed gas. In the Cartwheel, however, the collision has disturbed this gradient, producing a more complex picture of chemical distribution. At the nucleus, the oldest populations of stars show high metallicity consistent with repeated cycles of star formation and enrichment before the collision. Generations of stars lived and died here, scattering elements like oxygen, carbon, and iron into the surrounding gas. These metals became part of new stars, steadily raising the average metallicity of the central region. Even so, the nucleus is now quieter, its stars carry the memory of this long enrichment. Spectroscopy confirms strong absorption lines from heavy elements, showing that the core retains the signature of a mature galactic environment. Moving outward into the intermediate disk, the metallicity patterns become more irregular. Here, the collision mixed gas of different origins, redistributing enriched material from the core and combining it with more pristine reservoirs pulled in from the outskirts. The result is patchy enrichment, with some regions showing high metallicity, others significantly lower. These irregularities mirror the turbulence in stellar motions, reinforcing the picture of the intermediate disk as a zone of disruption. Chemical studies here provide key evidence that the collision did more than create rings. It stirred the entire disk, blending material and erasing the smooth gradients of the past. At the outer ring, where star formation is most intense, the metallicity is moderately enriched, but not as high as in the core. This makes sense, as much of the gas that fuels the ring comes from the galaxy's outskirts, which were less processed before the collision. Yet the new stars forming in the ring already contribute to enrichment, rapidly increasing the abundance of metals in the gas. Supernovae from massive stars scatter fresh elements into the medium, enriching it further with each generation. Observations show that metallicities in the ring are rising as the starburst continues, reflecting the rapid recycling of matter triggered by the density wave. This distribution, high metallicity in the core, patchy in the intermediate disk, moderate but rising in the ring, is a hallmark of collisional ring galaxies. It contrasts with undisturbed spirals where the gradient is smoother and more predictable. In the Cartwheel, the disrupted gradient tells astronomers how material has moved and how the galaxy is evolving chemically. It also provides constraints on the timescale of the collision. as the enrichment in the ring must have occurred within the last few 100 million years. This rapid change underscores the intensity of the starburst and the efficiency with which massive stars enrich their surroundings. The metallicity patterns also hold clues to the cartwheel's long-term evolution. If the starburst in the ring continues, it will eventually consume much of the available gas, leaving behind enriched stellar populations. The ring will fade in brightness as star formation declines, but the stars it produced will preserve their chemical signatures. Over billions of years, as orbits mix and the galaxy settles, these stars will spread, creating a more uniform distribution of metallicity across the disk. The current irregularities are thus temporary snapshots of a transitional phase between the spiral past and a future equilibrium. Another aspect revealed by chemical studies is the presence of gradients in specific elements. Ratios of oxygen to nitrogen, for example, indicate the relative contributions of different generations of stars. In the cartwheel, these ratios vary between regions, showing that some parts of the galaxy are dominated by enrichment from very massive stars, while others reflect longer-term contributions from intermediate mass stars. This variation reinforces the picture of patchiness created by collision, where different parts of the disk experience different histories of star formation and enrichment. The tidal debris fields also contribute to the chemical story. Gas and stars flung outward during the collision carry with them the metallicities of their origins. Some debris shows enrichment levels similar to the disk, while other parts are more pristine. This distribution reveals how material from different radii of the galaxy was scattered into space. If some of this debris forms tidal dwarf galaxies, their chemical composition will preserve a record of their parent state at the moment of collision, providing astronomers with a natural experiment in how galaxies share their matter with the cosmos. Understanding the chemical gradients of the cartwheel is not only important for reconstructing its history, but also for placing it in the broader context of galaxy evolution. Collisional ring systems are rare, but they illustrate how interactions accelerate the processes of enrichment. In a few 100 million years, the cartwheel's ring has produced and dispersed metals at a rate that might otherwise have taken much longer. This demonstrates how collisions act as engines of change, reshaping not only structure and motion, but also chemistry. The cartwheel stands as one of the clearest examples of this accelerated cycle. The future of the cartwheel is guided by these same chemical and structural processes. As the ring expands, it will eventually dissipate, and the galaxy will move toward a quieter phase. The metallicities of its stars and gas will continue to shift, trending toward greater uniformity as turbulence mixes material. The nucleus may remain enriched and quiet, while the outer regions will gradually inherit the metals produced in the current starburst. The galaxy may never return to its original spiral form, but it will find a new balance, its chemical record preserving the history of transformation. For astronomers, the cartwheel is not only a spectacle of light, but also a laboratory of matter. Its gradients in metallicity provide a map of how gas was redistributed, how stars enriched their environment, and how collision altered a galaxy's internal chemistry. By studying these patterns, scientists gain insight into the universal processes of stellar evolution and galactic interaction. The cartwheel's ring, spokes, debris and nucleus are visible features, but beneath them lies this invisible record of elements, the true currency of cosmic evolution. Thus, the Cartwheel Galaxy is more than its dramatic appearance. It is a system caught in the act of transformation, with its chemical gradients revealing both what it was and what it is becoming. The enriched core, the patchy intermediate disk, the rising metallicity of the rim, and the scattered debris beyond all speak to the consequences of a single collision. They mark the stages of disturbance, recovery, and renewal, ensuring that the cartwheel will remain not only a striking image, but also a key subject for understanding how galaxies live, change, and endure in the cosmos.